Okay, welcome to the deep dive. We've got a really interesting stack of material in front of us today, shared by you, our listener. And it really cuts right to the heart of a major challenge in our increasingly connected world, doesn't it?
It really does. This question of reliability of trust.
How do you build systems you can actually rely on when, those systems involve potentially millions of distributed devices all over the place?
Yeah, that distribution is key.
So that's our focus for this deep dive, the crucial topic of resilient IoT architecture. As more and more of our lives, our work, our critical infrastructure rely on these smart, connected things, well, understanding the underlying structure.
And particularly its ability to withstand chaos.
Right, exactly.
Right.
It isn't just important, it's becoming the absolute bedrock of trust and functionality.
That's precisely what this deep dive is all about. The material you provided is focused specifically on building a resilient IoT architecture, delving into the strategies needed for stability and scalability within these incredibly complex distributed networks of devices. And the sources emphasize that as the sheer number of connected devices and systems just explodes, and as they become integrated into more critical functions, well, the challenge ramps up significantly, ensuring these infrastructures can actually withstand all sorts of adverse conditions, simple network glitches, hardware failures, massive data surges, even sophisticated cyber threats.
It moves from being just a nice technical feature.
Exactly. It moves from a technical aspiration to a fundamental requirement. And it's clear the information here speaks to, well, a dual audience.
Right, developers and management.
Yeah, both the developers building the nuts and bolts and the technical management responsible for the strategy, the operations, and ultimately the success or failure of these systems out in the real world.
Absolutely. So our mission for this deep dive is to really pull out the core insights and the most actionable best practices from this stack of sources. We want to understand not just what makes an IoT architecture resilient, covering stability, scalability, security, but also how these technical considerations align with and are really driven by broader business goals, operational necessities.
Because it's much more than just preventing crashes, isn't it?
Way more. It's about designing systems that can fundamentally adapt, recover, and just keep functioning even when things go wrong.
Because in the real world, things inevitably do go wrong.
Always.
Precisely. So following the trajectory of the material, we'll start by grounding ourselves in what resilience specifically means in the unique context of IoT. From there, we'll unpack the foundational architectural components identified as essential. We'll explore how specific design patterns lend themselves to building robustness.
Like microservices and things like that.
Exactly. Then we shift focus to the increasingly vital role edge computing plays in distributing that resilience. The discussion then moves to the operational side, the absolute necessity of real-time monitoring and how it enables proactive measures like predictive maintenance.
Right, getting ahead of the problems.
And the sources also rightly bring in the human and external factors, the critical need for collaboration between technical teams and management.
Which sounds really interesting.
It is. And also the significant influence of the regulatory landscape. Finally, we'll look ahead to the future trends shaping how we'll continue to build more resilient IoT systems in the coming years.
Okay, let's jump right in then. The source material kicks off by posing that fundamental question. What does resilience actually mean when we're talking about IoT? We hear the word thrown around a lot, but getting a precise definition in this context feels like the right starting point.
It is, and the definition provided in the sources is concise, but, well, powerful. Resilience in IoT systems is the ability to continue operating under adverse conditions.
Okay, adverse conditions.
Yeah, and that seemingly simple phrase unpacks into a whole lot of complexity when you apply it to IoT. Adverse conditions in this world aren't just, simple server errors. They can be incredibly diverse. A sensor failing in some remote, inaccessible location.
Out in the field somewhere.
Right. Or a wireless network experiencing massive interference, a sudden unpredictable spike in the volume or velocity of data coming from devices. A cyber attack trying to disable or hijack devices.
Or even just extreme weather affecting the hardware.
Exactly. Environmental factors are huge. And the reason this is particularly challenging and absolutely critical in the IoT space, distinguishing it significantly from traditional IT systems, well, it's the inherently distributed and often physical nature of these deployments. You have devices potentially numbering in the thousands or millions, spread across vast geographical areas, or embedded within complex physical infrastructure.
Like factories or cities.
Precisely. They operate in incredibly varied and often challenging environments.
Yeah.
factories, farms, vehicles, harsh weather conditions,
Yeah.
and they have a fundamental reliance on connectivity.
Which can be shaky at best sometimes.
Totally. Cellular, Wi-Fi, satellite, LoRaWAN, whatever it is, it can be inherently unreliable, intermittent, or subject to external factors. So if even a small part of this geographically dispersed, highly interconnected, and physically integrated system fails, or if connectivity is lost to a segment of it, the system must be designed with mechanisms to either continue functioning locally, recover automatically and quickly, or at the very least, fail gracefully.
Without causing harm, right, or losing critical data.
Exactly, or collapse in the entire operation. This distributed vulnerability makes resilience just a paramount design consideration from day one.
That really emphasizes how different this is from just, say, keeping a central server online. It's about surviving failure out in the wild, literally.
hmm
The source material talks about the implications of system failures, downtime, data integrity issues in this context. It makes it clear these aren't minor glitches. What do those implications look like in the real world based on the seriousness the sources assign to them?
Well, the implications highlighted are profound precisely because IoT systems are so often intertwined with physical processes or critical human activities. It's not just numbers on a screen.
Right.
When an IoT system experiences failures, downtime, or data integrity issues, the consequences ripple out from technical problems into tangible, real-world disruptions. System failures can mean devices stop collecting crucial data. Imagine environmental sensors in a remote pipeline failing to report a leak,
Oh, wow.
or connected manufacturing equipment just stopping production cold.
Downtime in IoT isn't just frustrating then. In an industrial setting, it could mean an entire factory floor idles.
Resulting in colossal financial losses per hour. Yeah. In smart cities, non-resilient systems could lead to traffic management failures causing gridlock,
Public safety systems being unresponsive.
or utility grids experiencing instability. And data integrity issues, where data gets corrupted, lost, inaccurate, or tampered with,
Yeah.
that can be particularly dangerous.
Because decisions are made based on that data.
Exactly. If automated systems make decisions based on faulty data, like incorrect readings from medical sensors guiding patient care,
That's terrifying.
it is, or flawed data guiding autonomous vehicle navigation, the outcomes can be life-threatening or cause severe damage. The sources underline that because IoT connects the digital to the physical world, a failure in one seemingly small part, like a single faulty sensor or a gateway losing connection, doesn't just stay a localized digital problem.
It cascades.
It can have a devastating cascading effect throughout the entire system, or lead to significant, measurable, and often costly real-world consequences, consequences that go far beyond what we typically associate with, say, IT downtime.
It's the difference between a website being down and maybe a bridge sensor failing to report a structural issue.
Precisely that kind of difference in impact.
Wow, okay. That distinction really highlights the stakes involved. So resilience in IoT isn't just a technical best practice. It's directly tied to safety, reliability, and core business function. The source material connects this directly to user trust and business continuity. Why does resilience matter so much beyond just the internal technical operation?
This is where the material makes a really vital link. Unreliable IoT systems directly erode user trust and threaten business continuity. Think about it. If a connected consumer product, say a smart security system or a connected appliance, constantly glitches, drops offline, or provides inaccurate info,
You'd get fed up pretty quickly.
right, users will quickly lose confidence in the technology and the company behind it. They'll abandon the product, leave negative reviews, look for alternatives. Trust, once it's lost, is incredibly difficult to regain. And for businesses relying on IoT as a core part of their service or product offering, whether that's providing predictive maintenance for industrial equipment, managing a fleet of connected vehicles, offering smart home services, or delivering healthcare solutions, frequent failures or extended downtime mean they simply cannot deliver value to their customers.
It hits their bottom line directly.
Directly impacts their operational capability, leading to financial losses from lost revenue, damaged reputation, making it harder to attract new customers, and potentially even legal liabilities or regulatory penalties, especially in critical applications where downtime could cause harm.
Yeah.
So the source material makes it abundantly clear. Technical resilience isn't just about keeping the lights on in the server room. It is the fundamental technical enabler for a business to continue operating in the real world, to deliver its promised value and maintain the essential trust of its users and partners. Without a resilient foundation, the business itself is really built on shaky ground.
That connection makes perfect sense. The tech has to be reliable for the business to be reliable. Okay, so moving from the why to the how. What are the essential architectural components the source identifies? The building blocks for creating this kind of foundational resilience.
The material is quite specific here. It lists three core, indispensable components that must be woven into the fabric of any resilient IoT architecture right from the ground up.
Okay, what are they?
Redundancy, scalability, and security.
Redundancy, scalability, security. Got it.
And these are not features you bolt on later. They are fundamental design principles that should inform every choice you make when building the system.
Let's unpack redundancy first then. The source emphasizes its importance, particularly in network components. Why is having backups or alternative paths so crucial, especially where connectivity is involved? That seems like the weak link sometimes.
It often is. Redundancy, as outlined in the sources, is the principle of eliminating single points of failure.
Yeah.
In the context of IoT, which is inherently distributed and relies so heavily on communication, network components are often the most vulnerable links. We're talking about things like the gateways that aggregate data from many devices before sending it upstream.
Those collectors in the field.
Right. The communication links themselves, Wi-Fi access points, cellular modems, satellite links, etc., and the connections from those edge locations back to central cloud services. If you have only one gateway handling a large group of devices, and that gateway fails due to a hardware issue or a power outage, boom, all those devices lose their connection.
Right, everything downstream is cut off.
Exactly. If a single cellular provider loses coverage in a critical area, every device relying solely on that connection goes blind. So redundancy means having duplicate components or alternative pathways ready to take over instantly if the primary one fails.
Okay, so what does that look like in practice?
Well, drawing on general IoT knowledge to illustrate the source's point, this could mean having multiple gateways in a location with automatic failover if one goes down, or equipping devices or gateways with multiple types of connectivity like failover from Wi-Fi to cellular if Wi-Fi becomes unavailable.
Multi-homing, sort of?
Yeah, or designing network paths with multiple routes back to the cloud. The goal is to prevent a single component failure or a temporary network disruption from bringing down a critical segment of the system. It ensures continued operation and maintains stability even in the face of hardware malfunctions or unpredictable network conditions.
Got it. So it's like having multiple emergency exits and backup power sources, essentially. Okay, next. Scalability. The source places strong emphasis on designing for scalability from the onset. Why is that initial design phase so critical for scalability, and how does it contribute to resilience? Feels like something you could add later, maybe.
That's a common misconception. But the source is right to stress the onset part. Scalability is the system's ability to gracefully handle increasing load, whether that's a surge in data volume, a rapid increase in the number of connected devices, or more complex processing requirements, all without experiencing performance degradation, latency spikes, or outright failure. And the source's insistence on designing for it from the onset is absolutely crucial because, in most architectures, trying to retrofit scalability into a system that wasn't originally built for it is, well, it's incredibly difficult.
Okay.
Often prohibitively expensive, and usually requires a major disruptive overhaul. Think of building a small access road and then suddenly needing it to handle a 10-lane highway worth of traffic. The fundamental structure just isn't capable.
Right, you can't just widen it easily.
Exactly. In IoT, this means making early architectural decisions about communication protocols, data ingestion pipelines, database choices, processing frameworks, things that can handle not just the current load, but also significant anticipated future growth. Choosing a database that can scale horizontally, selecting messaging protocols that can handle high throughput, designing processing logic that can be easily distributed. These are examples of that upfront thinking.
And how does that early design contribute to stability and resilience?
Because a system that is not scalable will become inherently unstable as the load grows. It's almost guaranteed. Performance will degrade, response times will creep up, queues will back up, and components will eventually just crash under the stress of excessive demand.
So lack of scalability causes instability.
Precisely. By building scalability from day one, you prevent these stability issues from arising as your deployment expands. You ensure the system remains reliable and performs consistently, even as it grows dramatically. It's proactive stability management.
It makes sense that planning for growth prevents growing pains from becoming system-crippling problems. Okay, finally, security. The source highlights integrating security measures without compromising performance. This sounds like a classic balancing act, especially with those tiny, resource-constrained IoT devices.
It is indeed a significant challenge, and the sources correctly identify security not just as a separate concern, but as a vital component of resilience itself.
How so?
Well, a system that is insecure is inherently vulnerable to attacks, denial-of-service attacks that disable it, data breaches that compromise its integrity and user trust, or malicious control that could lead to physical harm. An insecure system isn't resilient because it's easily broken.
Right.
So robust security measures are essential. Strong device authentication to ensure only legitimate devices connect, encryption of data, both when it's being sent in transit and when it's stored at rest. Secure boot processes to prevent devices from running tampered software, mechanisms for securely updating firmware over the air to patch vulnerabilities, fine-grained access control. The list goes on.
But the tricky part is doing that on devices with limited power or processing.
Exactly. The difficulty, as the source implies, lies in implementing these robust measures on often resource-constrained IoT devices. Many edge devices have very limited processing power, tiny amounts of memory, and critically limited battery life. Heavy encryption algorithms or complex authentication handshakes consume significant CPU cycles, memory, and power. This can impact battery life, introduce unacceptable latency for real-time applications, or simply overload the device. Finding that right balance, implementing sufficient security without crippling the operational performance of the system is paramount for maintaining operational resilience.
Because a secure system that doesn't work isn't really resilient.
Precisely. A perfectly secure system that is too slow or drains batteries too fast to function is not resilient in a practical sense. Conversely, a fast, efficient system with weak security is just waiting to be compromised and disabled. So achieving that balance is absolutely key to ensuring the system isn't just theoretically secure, but remains secure and functional under real-world constraints and threats.
So it's about finding that sweet spot where security doesn't kill usability, but is robust enough to protect the system's ability to operate. Okay. Speaking of building the system, how do we actually design these resilient structures? The source material discusses design patterns. What specific patterns are highlighted as particularly effective for enhancing resilience in IoT?
Yeah, the source highlights a few key architectural patterns that offer significant advantages for resilience. It brings up the comparison between microservices and monolithic systems,
Oh, okay.
discusses the benefits of adopting an event-driven architecture, and emphasizes the role that containers and orchestration platforms play.
Let's start with microservices versus monolithic systems. For someone familiar with software development, they probably know the basic difference. But how does one potentially enhance resilience more than the other, specifically in an IoT context?
Right, so just quickly, a monolithic system is like a single, large, tightly integrated application where all functionalities are bundled together. Think of an older style application where device management, data processing, user interface, analytics may be all part of one big code base, deployed as one unit.
Okay.
A microservices architecture, in contrast, breaks the system down into a collection of small, independent services, each responsible for a specific business capability, like a service just for authenticating devices, another for processing sensor data, another for sending commands. These services communicate with each other over a network, often using APIs.
And the resilience benefit comes from?
Primarily through fault isolation. That's the key term the sources emphasize. In a monolithic system, a bug or failure in one module, if not contained perfectly, can potentially crash the entire application, bring down all functionality.
Right, one bad apple spoils the bunch.
Exactly. In a microservices architecture, because the services are independent and loosely coupled, a failure in one service, say, the service responsible for generating reports, is much less likely to affect other critical services like device connectivity or data ingestion. You might lose reporting capability temporarily, but the core function of collecting data and controlling devices can continue. This independent failure and, crucially, independent recovery model is a major resilience advantage.
So you can restart just the broken piece.
Right. If a microservice fails, it can often be restarted or replaced without affecting the rest of the system. Plus, microservices can be scaled independently. If your data ingestion service is bottlenecked, you can scale only that service, adding stability under load without over-provisioning other parts of the system. This granularity in failure handling and scaling makes the overall architecture much more robust to issues affecting individual components.
Okay, so breaking it down into smaller, contained units means an issue in one is less likely to take everything else down. That makes a lot of sense for a distributed system like IoT. Event-driven architecture is another pattern mentioned. How does that contribute to managing loads and adding resilience? Sounds a bit different.
It is a different approach. An event-driven architecture is a pattern where different parts of the system communicate by reacting to events that occur, rather than calling specific services or following a fixed process flow directly.
So, reacting to things happening.
Yeah, an event is simply a notification that something significant has happened. Device X has sent data. A threshold has been crossed. A command has been received. Components publish events, and other components subscribe to the types of events they care about.
And the resilience comes from?
The key resilience benefit highlighted here is decoupling and load management, often through intermediary mechanisms like messaging queues or brokers. When a device sends data, an event, it doesn't send it directly to the processing service. It sends it to an event broker or a queue. The processing service then picks up events from that queue when it's ready.
Ah, so there's a buffer in between.
Exactly. This decouples the producer, the device sending data, from the consumer, the service processing it. If there's a sudden burst of data from thousands of devices.
Which happens in IoT.
Oh, absolutely. The event queue acts as a buffer. It absorbs the incoming events, preventing the processing service from being instantly overwhelmed and crashing. The processing service can then process the events at its own pace, or you can scale up the number of processing instances to drain the queue faster if needed.
So it smooths out the peaks.
Precisely. This queuing mechanism provides significant resilience against unpredictable or spiky workloads, ensuring that downstream systems aren't overloaded and can continue operating stably even during peak demand or unexpected surges. It lets the system absorb shocks in data flow.
The queue as a shock absorber. I like that analogy. Okay, the source also brings up containers and orchestration, which are very common terms in modern infrastructure. Docker, Kubernetes. What specific role do they play in enhancing scalability and resilience, especially in an IoT deployment?
Right, so containers, like Docker, provide a way to package an application and all its dependencies, libraries, configuration files, everything into a single, lightweight, portable, and consistent unit.
Solves the "it works on my machine" problem.
Exactly that. It ensures an application runs reliably the same way regardless of where it's deployed, whether that's on an edge gateway, a local server, or in the cloud. And this consistency itself is a foundation for resilience because it reduces deployment errors.
Okay, so that's the container part. What about orchestration?
Orchestration platforms, with Kubernetes being the dominant example, are the engines that manage these containers at scale. And this is where the really significant resilience benefits come in. Orchestration automates the deployment, scaling, and management of containerized applications. For scalability, orchestration can automatically scale the number of container instances of a service up or down based on demand metrics.
Like CPU usage or maybe that queue length we talked about.
Exactly, ensuring the system maintains performance under varying loads. But for resilience, orchestration platforms are constantly monitoring the health of the running containers. If a container fails, becomes unresponsive, or exits unexpectedly, the orchestrator detects this and can automatically restart it or even replace it on a different machine if necessary.
So it's self-healing.
It provides automated self-healing, yes. It handles health checks, ensures the desired number of service instances are always running, and can automatically redistribute load away from unhealthy instances. This automated self-healing, scaling, and load balancing is incredibly powerful in dynamic IoT environments. It ensures that services remain available and performant even when individual containers or underlying infrastructure experiences issues. It provides an automated safety net and scaling mechanism.
So containers give us reliable, portable building blocks, and orchestration intelligently manages those blocks, healing them and scaling them automatically. That's a very clear contribution to operational stability. Shifting gears a bit now, the source highlights the increasing importance of edge computing. How does moving data processing and decision-making closer to the source, out on the edge of the network, specifically enhance the resilience of an IoT system?
Right. Edge computing represents a pretty fundamental shift from the traditional model, where, almost all data processing and analytics happen centrally in a large cloud data center. With edge computing, processing power is strategically placed much closer to where the data is generated. This could be directly on the IoT device itself, or maybe on a nearby gateway or server in a factory, a vehicle, or building.
Closer to the action.
Exactly. And the source explicitly notes that this approach significantly enhances both efficiency and reliability. And reliability in this context is really a direct synonym for resilience.
Okay, one major benefit mentioned is reducing latency. How does minimizing the time lag between data generation and processing directly tie into resilience?
Latency is that delay inherent in transmitting data and getting a response back. In a pure cloud model, a device collects data, sends it potentially thousands of miles to a cloud data center. The data is processed, a decision is made, and an action command might be sent back to the device or another system. This round trip can introduce significant delays, tens or hundreds of milliseconds, even seconds with unreliable connections.
Hmm.
The source points out that processing critical data at the edge drastically reduces this latency because the data doesn't have to travel far, if at all, for certain decisions.
And why is low latency essential for resilience?
Because many critical IoT applications require near real-time responsiveness to function safely and effectively. Think of autonomous systems like vehicles or industrial robots, where decisions need to be made instantly based on sensor input.
Or medical monitoring?
Exactly. Real-time patient monitoring where immediate alerts are necessary. Or relying on a potentially unstable or high-latency connection to a distant cloud for these critical decisions makes the system inherently fragile. Any network congestion, temporary outage, or increased cloud processing load can introduce delays that make the application unreliable or even dangerous.
So the edge processing avoids that dependency.
Yes. By processing at the edge, these critical, time-sensitive decisions can be made locally, without dependence on the cloud connection. This dramatically improves the system's responsiveness and its ability to function reliably, even when the connection to the wider internet or central cloud is unstable or unavailable. It makes it far more resilient to network fluctuations.
Okay, beyond latency, the source mentions decentralizing processing to mitigate risks. What specific risks are we mitigating by moving processing away from that single central point?
The primary risk mitigated by pushing processing and intelligence to the edge, as highlighted in the material, is the risk of a single point of failure. Specifically, the failure associated with a central cloud service or a sole dependency on cloud connectivity.
Even big clouds go down sometimes.
Exactly. Even the most robust cloud providers can experience regional outages. And the network connections from edge locations back to the cloud can be subject to all sorts of local issues: physical cable cuts, cellular tower problems, Wi-Fi interference, ISP failures. If your entire system's brain is in the cloud, losing that connection effectively, well, it lobotomizes your deployment in the field.
Yeah, the devices become dumb terminals.
Pretty much. By decentralizing processing to the edge devices or local gateways, you distribute that intelligence and capability. Critical functions, data filtering, local control loops, even basic analytics can continue to run autonomously at the edge, even if the connection back to the central cloud is lost.
So things keep working locally.
Right. The edge devices might buffer data to sync later, but they can still perform their core, safety-critical, or time-sensitive tasks. This distribution means that an outage affecting the central cloud, or the network connecting to it, doesn't necessarily cripple the entire system. It provides a layer of operational resilience that a purely centralized cloud architecture just cannot match. It ensures local survivability.
That makes sense. Don't put all your processing eggs in one basket if you need things to keep running locally, especially critical things. The source mentions real-world applications and success stories for edge computing and resilience. While we don't have the specific examples from the source here, what types of scenarios would these likely illustrate, building on the points we've just discussed?
Based on those advantages, reduced latency and decentralized processing, these success stories would very likely showcase scenarios where edge computing enabled an IoT system to maintain.
A case study might illustrate how local processing on medical devices or within a hospital network ensured real-time patient data processing and critical alerts continued, even if the external internet connection failed, avoiding delays in patient care.
Makes sense.
In the energy sector, maybe an example of local grid controllers at a substation managing power flow based on local sensor data during a communications outage, preventing a wider blackout. The common thread in these success stories would be edge computing, providing that essential layer of local autonomy and responsiveness. That allows the system to remain functional and resilient when challenged by the unpredictable nature of distributed deployments and those network dependencies.
Okay, so edge computing provides that crucial layer of local independence for resilience. Now, the source material really emphasizes that simply building a resilient system isn't enough. You absolutely have to actively monitor and manage it. How do real-time monitoring tools and the analytics applied to that data significantly boost the resilience of an IoT architecture in practice? It's not just build and forget. You're exactly right. It's definitely not build and forget. Building resilience is the design phase, but maintaining it and responding to potential issues is the operational phase, and that requires constant vigilance. The source highlights that continuous real-time monitoring, provides the essential nervous system for your distributed IoT deployment. It gives you visibility.
Seeing what's actually happening out there.
Precisely. Into the system's health, performance, and state at any given moment. This isn't just about collecting vast quantities of raw data from devices. It's about having the tools and processes in place to aggregate, analyze, and crucially, act upon that data quickly. This allows operators and increasingly automated systems to detect issues as they happen across potentially millions of distributed endpoints.
Okay, so what kind of key metrics are we talking about here? What sort of information should be on that monitoring dashboard to effectively manage resilience in an IoT system based on what the sources are implying?
Well, drawing from the critical aspects of IoT system health and operation implied by the source's focus on reliability and stability, the key metrics you'd be monitoring are incredibly diverse. They really span devices, connectivity, data flow, and processing.
Give me some examples.
Okay, on the device level, simple but vital things. Device connectivity status is online or offline. Battery levels, if applicable, maybe device temperature, error logs. At the connectivity layer, you'd track signal strength, data throughput, packet loss rates, latency for each connection type and device. For data flow, monitoring ingestion rates, message queue lengths like we talked about with event-driven systems, data processing times, data validation errors. That's crucial. On the processing infrastructure, whether it's edge or cloud, you'd watch CPU load, memory usage, disk I/O, and application-level metrics like error rates and response times for your microservices.
And security events, too, presumably.
Absolutely fundamental. Security-related metrics, such as failed authentication attempts, access denials, or logs of unusual activity, are critical for detecting potential breaches that could impact resilience. Essentially, you're monitoring anything that tells you if a component is healthy, performing within expected parameters, and communicating effectively. Monitoring this wide array of metrics from every part of the system provides that rich data stream needed to understand the system's status and identify deviations that might indicate an issue is developing.
That sounds like a huge amount of data points to keep track of. And how does monitoring all those real-time metrics feed into the concept of predictive maintenance that the source mentions as a resilience strategy? How do you get from data to prediction?
This is where the analytics part of real-time monitoring becomes incredibly powerful for resilience. By analyzing not just the current state, like is a device online right now, but also the historical trend data from those key metrics, you can start to identify patterns, anomalies, and correlations that indicate a potential failure is likely to occur in the future before it actually happens and causes an outage.
Ah, okay. Seeing the signs early.
Exactly. This is the essence of predictive maintenance. Instead of simply reacting to a failure after it has already occurred, which is reactive maintenance and disruptive for system, you use the data to predict when a component, device, or subsystem is likely to fail. And then you perform maintenance or intervention proactively.
Can you give an example?
Sure. Machine learning algorithms could analyze sensor data from a piece of industrial equipment, maybe detect subtle changes in vibration, temperature, or power consumption patterns that correlate with known precursors to failure for that type of machine. Or, in a connected vehicle, monitoring battery voltage fluctuations or certain error codes over time might predict the failure of a specific component before it leaves someone stranded.
Right.
In a communication network, consistently high latency or packet loss on a specific link, even if it's not yet causing complete failure, might predict an impending network outage or hardware failure. By identifying these patterns and predicting the failure, you can schedule maintenance, replace a faulty device during a planned service window, deploy a software update, or adjust configuration before the issue escalates into a system-wide problem.
So it changes how you manage resilience.
Fundamentally, it shifts your resilience strategy from being primarily reactive, recovering quickly from failure, to being significantly proactive, preventing failures from happening in the first place, which is obviously a far more desirable and robust state for critical IoT systems.
So, using data science to get ahead of potential problems before they bite you. The source mentions case studies where real-time insights have prevented failures. Again, without having the specific examples in front of us, what's the core demonstration these kinds of case studies would typically provide about the value of monitoring for resilience?
These case studies would be the concrete, often compelling examples demonstrating the tangible value of this proactive approach. They would likely show how a company implementing robust real-time monitoring and analytics was alerted to an anomaly or developing trend identified by the system. Maybe a subtle deviation in temperature, a gradual increase in error rates from a specific batch of devices, or a network link showing unusual behavior during off-peak hours, something a human might easily miss. This alert, triggered by the predictive analysis of real-time data, prompted human operators, or perhaps automated systems, to investigate. The investigation would then uncover an issue that, had it gone undetected, would have led to a significant failure, like a critical component overheating, a software bug consuming resources and eventually crashing a service, or a network infrastructure issue causing an eventual outage.
And the intervention prevented that.
Exactly. By intervening before the predicted failure materialized, replacing the component, deploying a patch, rerouting network traffic, they averted a major incident, proving that the investment in monitoring and analytics directly prevented costly downtime, safety hazards, or data loss. They demonstrate the ROI and the practical power of using data to anticipate and prevent disruptions, directly contributing to overall system resilience.
That really drives home the point that monitoring is not just reporting after the fact, it's actively preventing failures.
Okay, now this is interesting. The source material also delves into the human element, specifically highlighting the importance of collaboration between development teams and technical management. Why is this cultural aspect of collaboration so crucial for successfully building truly resilient IoT solutions? It seems less about code and more about people talking.
You're right, it might seem less technical on the surface, but the source highlights a crucial, often overlooked point. Technical resilience in IoT isn't purely a matter of writing robust code or deploying redundant hardware. It's not just an engineering problem. Building a system that can reliably operate under adverse conditions requires a deep, ongoing synergy between the teams building the system development, engineering, and the teams responsible for its strategic direction, operational context, resource allocation, and real-world performance expectations, technical management operations.
Different perspectives. Very different, but complementary. Development teams understand the technical possibilities, the limitations, the complexities of different architectures and technologies. Management understands the business impact of failures, the required levels of availability and performance, the cost constraints, the regulatory landscape, the overall strategic goals the IoT system is meant to achieve. Effective collaboration ensures that the technical solutions designed and implemented by development teams actually align with and meet the actual resilience needs of the business, as defined and understood by management. It prevents situations where engineers might say over-engineer resilience features that aren't actually critical for this particular business case, or, more dangerously, under-engineer resilience in areas that are absolutely vital.
So it bridges the gap between tech and business needs.
Exactly. It bridges the gap between what's technically possible and what's operationally necessary for the business to succeed with this IoT deployment.
Okay, so it's about ensuring the technical build serves the real-world operational requirements. What kind of communication strategies are highlighted as key to fostering this kind of effective collaboration and avoiding those misalignments or silos?
Well, the source implies the need for strategies that break down those silos and create a continuous loop of shared understanding and feedback between these groups. It's got to be more than just occasional meetings.
Right.
It suggests strategies like joint planning sessions right at the outset of projects, where both development and management are involved in defining requirements, discussing architectural choices, and really understanding the trade-offs involved in achieving different levels of resilience. Clear, accessible documentation that explains the architecture, its intended resilience features, and how it handles failures. That's crucial for management to understand what's actually being built.
Common ground.
Yes, and using shared dashboards and metrics that provide both teams with the same real-time view of system health and performance creates that common ground for discussion and decision-making. And establishing regular feedback loops, perhaps through dedicated forums or reporting structures, allows developers to communicate technical challenges or unexpected findings related to resilience back to management. And importantly, for management to provide updated insights from the field or shifting business priorities back to development. It's about creating an environment of transparency and shared responsibility for resilience outcomes.
How does this focus on aligning technical choices with business objectives, facilitated by this collaboration, specifically contribute to building a more resilient system in the end?
This alignment is fundamental to building appropriately resilient systems. Business objectives define the stakes, right?
Yep.
An IoT system managing a national power grid has vastly different resilience requirements. Near zero downtime must be fail-safe than, say, a system monitoring soil moisture in a non-critical agricultural application, where some downtime might be perfectly acceptable.
Hmm. Different levels of risk.
Exactly. And technical choices have costs attached, implementing high levels of redundancy, choosing complex microservices architectures, deploying advanced edge computing, investing in sophisticated monitoring platforms all requires significant resources, time, money, expertise.
When technical choices are aligned with business objectives through collaboration, you ensure that resources are allocated effectively to build resilience where it matters most for that specific business. You avoid overspending on unnecessary resilience features in non-critical areas while potentially neglecting critical areas. This ensures the system is not just technically sound, but also economically viable and designed to protect the business from the most impactful types of failures. That contributes to the overall sustainability and operational resilience of a whole venture relying on the IoT technology. And the source also mentions balancing encouraging innovation while maintaining standards. How is that delicate balance struck through collaboration, and why is it important for long-term resilience? Sounds like a tightrope walk.
It is a classic tension in technology, and it's particularly relevant in the fast-moving IoT world. Innovation brings new tools, protocols, approaches that could potentially enhance resilience, maybe a new encryption method, a more efficient communication protocol, a novel way to deploy edge processing.
Sup developers get excited about.
Often, yes.
Yeah.
Development teams are often eager to explore and adopt these. However, unchecked innovation without standards can lead to a fragmented, complex, and difficult to manage system, which paradoxically reduces resilience. A lack of consistent security practices, incompatible protocols, or diverse, unmanaged deployment methods across a large IoT fleet creates vulnerabilities and makes it much harder to monitor, maintain, and recover the system when things go wrong.
So standards provide the guardrails.
Yeah.
Exactly. Standards provide necessary guidelines for security practices, interoperability, deployment procedures, coding practices, technology choices. Collaboration helps strike this balance. Development teams can explore and propose innovative solutions, that's the innovation part, but these are evaluated against established or evolving standards defined jointly with management and operations, that's maintaining standards. This ensures that promising new technologies are adopted, but only in a way that integrates securely and maintainably into the overall architecture, enhancing resilience rather than undermining it through complexity or inconsistency. It's about controlled innovation guided by the need for stability.
So collaboration helps channel innovation into strengthening the system rather than just adding new, potentially disruptive elements. Okay. Another significant external factor the source brings up is the regulatory landscape. Why is understanding and actively addressing regulations absolutely essential for building resilient IoT applications beyond just, avoiding legal trouble? You're right to say it's more than just avoiding legal trouble, although that's certainly a big part of it. The source emphasizes that understanding the regulatory landscape is essential for resilience because regulations often directly mandate specific requirements. Requirements related to security, privacy, reliability, data handling. Things that are fundamental to the resilience of an IoT system. These requirements aren't optional suggestions, they are legal obligations. Noncompliance doesn't just risk fines or lawsuits. It can lead to forced system shutdowns, loss of licenses to operate, massive reputational damage, all of which fundamentally impact a business's ability to operate. It hits its resilience right at the core.
Especially in certain industries.
Particularly in highly regulated industries like healthcare, finance, energy, transportation. Regulations often specify required uptime levels, data retention policies, security controls like specific encryption standards or access logging requirements, and audit trails. Building a technically sound system is necessary, but if it fails to meet these mandated requirements, it's not truly resilient in the long term because its very operation is legally precarious and subject to external enforcement that could just disable it.
Okay, what kind of current regulations are typically impacting IoT deployments, broadly speaking, based on the themes in the source? What areas do they cover?
Based on the general context of building resilient systems and the critical nature of data in IoT, the types of regulations affecting deployments typically fall into several key categories. Data protection and privacy regulations are paramount, given the sheer volume and potential sensitivity of data collected by IoT devices.
Like GDPR.
Exactly. While the source might not name specific laws, the requirements would align with principles found in comprehensive data privacy laws, like GDPR in Europe, CCPA in California, or similar regulations emerging globally. These impose strict rules on how data is collected, processed, stored, secured, requiring specific resilience-enhancing technical controls like encryption, access controls, breach notification mechanisms, data anonymization, or deletion capabilities.
And industry-specific rules.
Yes, industry-specific regulations are also critical. Medical IoT devices must comply with health data privacy and device safety standards. Think IPAPA in the US or the MDR in Europe. Industrial IoT and critical infrastructure might fall under cybersecurity regulations or standards for operational technology resilience, like NERC CIP in North America for the power grid. Financial IoT applications face strict financial industry compliance related to transaction security and data integrity. The source's main point is that these varied regulations impose non-negotiable constraints and requirements that must be incorporated into the IoT architecture design from the very beginning.
To ensure the system can legally and safely operate.
Precisely.
And what about compliance strategies to avoid penalties?
Yeah.
How do organizations proactively ensure their IoT architecture meets these often complex regulatory requirements? It sounds like a job in itself.
It often is. The sources imply that compliance needs to be a proactive, integrated part of the development and operation lifecycle, definitely not an afterthought tacked on at the end. Key strategies would involve, first, thoroughly identifying all relevant regulations for your specific IoT application and the geographies where it will operate. This often requires legal and domain expertise in addition to technical knowledge.
Knowing the rules of the game.
Exactly. Then, incorporating compliance requirements directly into the system's design phase. This means selecting architectures, technologies, security controls that inherently support those regulatory mandates. Implementing the necessary technical controls is non-negotiable, robust encryption for data in transit and at rest, secure access management, detailed logging and audit trails, data retention and deletion policies that comply with privacy laws, secure software update mechanisms.
And checking it regularly.
Yes. Regular internal and perhaps external audits are essential to verify that the system remains compliant as it evolves and, importantly, as regulations themselves change. And maintaining comprehensive documentation detailing how the system meets specific regulatory requirements is also crucial for demonstrating compliance to authorities if needed. It's a continuous effort involving technical, legal, and operational teams working together.
And there's that balance again, right? The source mentions the balance between innovation and regulatory requirements.
Yeah.
How does that play out?
Absolutely. Regulation can sometimes feel like a constraint on technical innovation because it imposes rules, adds complexity, and can slow down time to market. Developing compliant features often requires more effort and adherence to specific, sometimes less cutting-edge standards or processes. However, the source implicitly highlights that regulation also serves a vital purpose. It drives the adoption of fundamental practices like security by design, privacy by design, and robust data management. Practices that are inherently resilience-enhancing. By forcing developers to think deeply about security, data integrity, system reliability right from the outset, regulations actually push the industry towards building more trustworthy and inherently robust systems overall.
So it raises the bar for everyone.
In many ways, yes. The challenge, and where collaboration and careful design come in, is finding solutions that meet these necessary regulatory requirements while still allowing for the integration of innovative technologies that can further enhance resilience in compliant ways. It ensures a baseline of essential resilience and responsible system design.
So regulations act as a necessary framework that pushes the industry towards safer, more reliable systems, even if they add complexity. Okay, finally, the source looks ahead, touching on the future. What trends are shaping how we'll build resilient IoT architectures in the coming years? What's on the horizon according to this material?
Yeah, the sources suggest that the landscape of IoT resilience is definitely dynamic. It's not a solved problem. As the scale, complexity, and criticality of IoT deployments continue to increase, and as the threats evolve, well, the approaches to building resilience must also evolve. Emerging technologies and changing demands will continue to push the boundaries of what's possible and what's necessary for stable, reliable systems.
What emerging technologies does the source imply might play a significant role in boosting IoT resilience in the future? Any specific hints?
Based on the material's focus on things like distribution, security, and automation, several emerging technologies could significantly enhance resilience. We might see greater adoption of, say, self-healing network protocols or advanced mesh networking capabilities that allow devices or network segments to automatically reroute communication around points of failure or congestion, making the network itself more resilient.
Smarter networks.
Smarter, more adaptive networks, yes. Advancements in distributed ledger technology, like blockchain, could play a role in creating immutable, tamper-proof records of device identities, data provenance, or transaction logs, enhancing trust and resilience against data tampering or counterfeit devices. New, more robust, and potentially interference-resistant wireless communication technologies could improve connectivity resilience in challenging environments.
And maybe changes in the hardware itself.
That too. We can see hardware-level advancements like processors with built-in redundancy or more sophisticated security features baked right into the silicon, making individual devices more inherently fault-tolerant and secure from the ground up.
The source specifically mentions the influence of AI and machine learning. We touched on this with predictive maintenance, but how else might these technologies impact the future of IoT resilience?
AI and machine learning are really poised to have a transformative impact on IoT resilience, going well beyond just predictive maintenance, although enhancing that is huge too. Their ability to process and find patterns in massive volumes of real-time data far exceeds human capabilities. AML algorithms can detect incredibly subtle anomalies, predict failures with higher accuracy, and potentially further lead time by analyzing complex multivariate data streams. And they can identify unusual system behavior that could indicate a security breach or an impending operational issue much faster.
But can they do anything about it?
That's the next step. Crucially, AML can enable automated response. Instead of just alerting a human operator, AI could potentially trigger automated remediation actions. Things like rerouting network traffic automatically, isolating a potentially compromised device from the network, restarting a failing service, or dynamically adjusting system parameters to prevent an overload before it actually causes a problem.
So the system starts managing itself more.
It's exactly. They can optimize system performance and resource allocation dynamically to maintain stability under unforeseen conditions. This allows for a transition towards more intelligent, self-monitoring, self-optimizing, and ultimately self-healing IoT systems. Moving beyond prediction to automated prevention and recovery, it makes the system inherently more adaptable and robust in the face of dynamic and unpredictable challenges.
That sounds like a significant leap forward systems that can essentially manage and heal themselves to a much greater degree. Finally, the source makes predictions for the next decade in IoT resilience and architecture. What's the overarching outlook based on these trends? What's the big picture?
Summing up the direction implied by the source's look at future trends and the increasing demands on IoT, the outlook for the next decade in IoT resilience and architecture points towards systems that are significantly more decentralized, far more intelligent, and substantially more automated. Architectures will likely push even more processing and intelligence out to the edge to maximize responsiveness and minimize dependence on central connectivity. AI and machine learning will become increasingly integrated, moving beyond simple analytics to drive sophisticated monitoring, predictive capabilities, and those automated self-healing responses we just talked about.
And security.
Security will continue its evolution towards being fundamentally embedded into the design process, from the lowest levels, the hardware, right up to the applications and data management. Security by design becomes the default, and the manual effort required to manage, scale, and maintain the resilience of vast IoT fleets will likely be drastically reduced through advanced orchestration and AI-driven automation. The expectation will simply be that as IoT becomes ubiquitous and truly mission-critical, the underlying architectures must provide unprecedented levels of reliability, availability, and security, designed to withstand an ever-widening array of potential challenges. Resilience becomes table stakes.
Wow, that was quite a deep dive into the source material on resilient IoT architecture. A lot to unpack there. We started by defining what resilience even means in this complex, distributed world of IoT. Explored the fundamental building blocks like redundancy, scalability, and security.
The three pillars.
Right. And saw how architectural choices like microservices, event-driven systems, and the strategic use of edge computing provide key design patterns for building in robustness.
Yeah.
We understood the absolute necessity of constant monitoring and how it enables predictive maintenance, highlighting that getting ahead of problems is really key.
Moving from reactive to proactive.
Exactly. And it's clear that the human element of collaboration and the external pressures of regulation are just as critical as the technical design in building systems that are truly reliable and trustworthy in the long run.
Exactly. I think the most critical takeaways from this deep dive really reinforce that building for stability, scalability, and security in IoT isn't just about meeting some technical requirements checklist. Yeah. It is absolutely fundamental to mitigating operational risks, ensuring business continuity, and building that essential trust with users and stakeholders. Redundancy protects against single points of failure. Real-time monitoring and predictive maintenance enable proactive problem solving. Regulatory compliance ensures the system can operate legally and responsibly. And strong collaboration ensures the technical design actually meets the real-world business needs for resilience. It's really an integrated effort across technology, process, and people.
Hopefully, this deep dive has provided those key nuggets and insightful aha moments from the source material, giving you, our listener, a clearer understanding of the critical considerations for building resilient IoT architectures without feeling overwhelmed by the sheer volume of information out there.
And as we look at the rapid evolution of IoT, its increasing integration into, well, every facet of our lives, and the growing sophistication of the challenges it faces, from technical malfunctions to increasingly clever cyber threats and complex environmental interactions, the concept of resilience becomes ever more paramount. So given this accelerating pace of change and the increasing sophistication of potential disruptions, here's something maybe to ponder further. What fundamentally new approaches or paradigms for resilience might be needed in the near future that go beyond the strategies we've discussed here today? Could we be moving towards systems that possess entirely new levels of self-awareness, adaptability, or even a form of, say, digital immunity against unforeseen threats? And what might the implications, perhaps even the ethical implications, of such highly autonomous resilience be?
Something to think about as the connected world continues to evolve rapidly around us. Thanks for joining us for this deep dive.